Good morning, everyone.
Morning.
So,
Morning.
first things first here, I want to apologize. I don't have all
Morning.
the exams graded. I started grading them, but yesterday was my first day on campus, and so I went to go teach classes. And last week, I bought a brand new laptop because the one I had was very old. So I got a laptop, got it all set up. You know how it is when you get a new laptop, you have to, install all the software you want, get everything set up. So I spent the whole weekend doing that, and then went to my class and opened my laptop up, and it wouldn't come on. And so my laptop was completely dead, and I talked to the manufacturer, it was defective. And so I spent all of yesterday trying to get a new laptop, and then spent last night doing that, getting it all set up. So I did not get to your test. Normally I'll have them graded within, like, by the next time we meet, but it was an exception. So I apologize ahead of time. I should get those graded by the end of the day. All right. So just keep an eye on your grades. Some of you already have your grade. When you go and you look at your grade, you should be able to click on the grade, and you should see the actual exam attached to the grade, and you can open it and you can see what problems you missed. Like, you can see what I've marked on the test. All right. So just FYI, any questions on that? No. Okay. And we still have at least one student that needs to take the test still. So, I won't talk about the test yet. I'll talk about it later. But what we're going to do is we're going to move on. And I've decided to make a slight change. Well, it's going to look like a drastic change, but we're going to change the order in which we're going to cover the topics for this class. And I think it's just because it'll flow a little better. A lot of what we've been doing has been algebra, manipulating expressions and things like that. So I think what we do next, we should continue with that theme. So what we're going to do on our schedule is we're going to finish up today. We're going to finish up the GCF part of this section. And then we are not going to go to percents, proportions, and all of that. What we're going to do is we're going to skip through. We're not going to do the scientific notation and conversions. We're not going to do that. We're going to go right to lines. Now, we will go back to this, okay? We will do it. It's just we're going to do this at the end. All right, so every day when we finish class, I'll tell you exactly what to do for homework. Please pay attention to that, because I don't want you going and just thinking, oh, we're just doing the next thing on the schedule, because you'll be doing stuff we haven't talked about. All right. So with that said, let's continue with what we were talking about before, which was greatest common factor. Or we hadn't talked about it, but we were about to. So there were a few problems on the test that had to do with these two problems. So I thought we would start class by taking a look at these two. Let's get this here. Copy this and start. Oops. Oh, and you know what? For the most part, almost all of you were able to get me a copy of their, you know how you're supposed to send me the test as a single PDF file. I can't remember a time where I've had so many people do it correctly. So I appreciate you all taking time to learn that and figure it out before the test, because I mean, everyone sent nice single files, and it's made it so much easier to grade. So, okay, so we're gonna do these two problems, and then when you look at your homework for these, hopefully it'll make a little more sense. So it says here for number 17, write the polynomial that represents the total volume of the rectangular prism shown below. Use the formula volume equals length times width times height. So this is a formula that you may be familiar with. If you have a box, or like a shoebox shape, that's called a rectangular prism, then the volume of it is always going to be the length times the width times the height. So length, width, and then the height. You just have to multiply those three things together, and that'll give you the volume. And the volume of something is how much it holds, right? Like if I measure the length of something, like how long my arm is, that's a length, right? But a volume is a measurement of how much is in something. So I have a cup here. The volume is how much liquid I can put in here. So to measure that for a box, you just multiply these three sides together. So that's what they want us to do. They want us to take the length, the width, the height, and multiply those three together. And what we're going to get is a polynomial that represents the volume. So I'm just going to write down that volume equals, and let me just put these here, x plus 1 times x times 4x. I just need to multiply those together. So the first thing I'm going to do is multiply the x and the 4x together. That should give me what? What's x times 4x?
4x squared.
4x squared. Okay, so I have that. And then to get the 4x squared to multiply times the x plus 1, I have to distribute it through the parentheses. So I multiply 4x squared by x. That should give me 4x cubed. And then 4x squared times 1 should just give me 4x squared. And that is it. So your answer is a polynomial. That's what they're referring to here. This idea of a polynomial, that's what this is. That polynomial represents the volume of this box. So if they had given us numbers like, 5, 3, and 8, something like that, we just multiply the numbers together, no problem. But if they give us variable expressions like this, then our answer is going to contain variables in it also. Is that clear? Any questions on that? Okay, let's look at the next part. Number 18. A countertop pictured below will have a hole drilled to hold a utensil holder. The area of the entire countertop is given by this polynomial. So they're telling you right now that this represents the area, okay, of the countertop, of the entire countertop without a hole. So this is without the hole. So if we take the countertop, they're telling us that the area of this is that, right? And then they're telling us that the area of the hole is given by that equation. So if you look at just the hole, they're saying that the area of this is that. And then they tell you to write the expression or write an expression for the area of the countertop that remains after the hole is drilled out. So what do you need to do there?
Subtract, possibly.
Subtract, right? You want to take this area of the countertop, you want to take that area, right? The area of the counter, and subtract from it the area of the hole, right? Which is this part. If you take the area of the whole countertop and then take the hole out of it, the area of the hole, then that should give you the area of this thing, right? And since they gave us the expressions for each, I can just write down the area of the counter is 3x squared plus 12x plus 4. And from that, I want to subtract the x squared plus 2x plus 1. And most of you did pretty good on this part on the test. I think I can remember, I've only graded, I think, like half the class. So I think I remember maybe one student that kind of messed up this minus sign. You have to distribute the minus through the parentheses. And then on the first one, because there's a 1 here, there's nothing to distribute. So you can just rewrite the original expression. And then this becomes minus x squared minus 2x minus 1. And then at that point, you just collect like terms together. So how many x squareds will I have?
2.
2, right? I take that, subtract, so I get 2x squareds. How many x's do I have?
10.
10. Okay, so that's 12x take away 2x, so that's 10x. And then finally, 4 take away 1, we get 3. So this would represent the area of that. All this problem is doing is making sure you know how to subtract 2 polynomials.
Wait,
Well,
so would it be 14x or would it be, oh, my bad. Because wouldn't it be adding actually? If it's a minus and then another minus 2?
Um,
Oh, wait, no, never mind.
yeah, the
I
minus
was
2.
looking at it wrong.
Okay,
Okay.
you're good then?
Yes.
Okay. Okay, hold on. I've got to sneeze. Okay, sorry about that. All right, so let's move on to the next idea here in this section. And that is this thing called GCF. All right. And I'm not going to just jump right into this. I want to have a short discussion about what factoring is. We've been doing a little bit of factoring, but I want to make sure everyone is clear on what factoring is. All right. So look, the idea of factoring is very simple. It's a simple concept. It's hard to execute. All right. So let me give you an example. Let's say we take the number 15. All right. Can you think of 2 numbers that multiply to be 15?
3 times 5.
3 times 5. Okay. This is what we call the prime factorization of that number. And it turns out that every number can be broken down like this, unless the number itself is a prime number. A prime number, there's an infinite number of prime numbers, but if you take a number like 7, the only way you can break down 7 is if you do 1 times 7. So there's no way to break it down into 2 numbers that are something other than the 7 itself. So this is called a prime number. And then this is what we call a composite number, because it is composed of 2 other numbers. So the process of going from here to here is called factoring. We are taking something, breaking it down into 2 pieces that are multiplied together, right? That's what factoring is. And for numbers, it's not that difficult to do. Well, for small numbers, it's not that hard to do. For big numbers, it's very hard to do. Okay. In fact, and I'm going off topic here, if I give you a really big number, like 3, 4, 7, 8, 9, 0, 5, 1, 4, 2, and I ask you to break it down and try and break it down into 2 prime numbers, very hard to do. Very, very difficult. Now, all of, when you log on to your bank account and you get into your bank and you're looking at your money and stuff, and they tell you it's encrypted, right? Encryption, all encryption is based upon that simple idea, is that if you take a very large number, you try and break it down into 2 numbers, all right? What banks use is what they do is they start with 2 numbers that they know, and these are 40 digits long. 40 digits. So imagine a number that's 40 digits long. And they multiply those 2 40-digit numbers together, and that gets you an 80-digit number. And that 80-digit number is kind of like the code. I'm simplifying this. I'm trying to make this very simple because I don't want to get into this. All right. But that code, if somebody could break that code, if somebody could somehow, take this, multiply those 2 together, you're going to have an 80-digit number. If someone could take that 80-digit number and easily get back to the 2 40-digit numbers, if they could do it, you could break encryption and nothing would be safe. Our bank accounts, our personal information, nothing would be safe. But the process of doing that is so hard, even if you had every computer on the planet trying to figure it out, it would take the age of the universe to figure it out. It's that hard to do.
So is that kind of like how like cryptocurrency would work then? Because I know they use where it's like encrypted like that or something like that.
All encryption is based upon this idea. Okay, and we have not figured out a way to do it fast. Look, if somebody figures this out, we're all screwed. Like everything's coming down because nothing's safe anymore. Electronically, nothing's safe. And then see, the thing is, even as computers get faster, it doesn't matter because what we can do is just use bigger numbers. So instead of using 40-digit numbers, then you start using 80-digit numbers and multiply them together, you have a 160-digit number. And then the computers are going to have problems with that because it's so much more it has to do. So it's a very simple concept, but it's very hard to do for numbers. It's kind of cool if you think about it. I mean, it's kind of scary too, but no one's been able to figure it out. There's no algorithm for it. It's just you have to do it by brute force. And yeah, so it's kind of a good thing, I guess, because we have protected our websites and stuff, or all our information. You've probably heard how, like, I don't know, a few years ago, I remember hearing in the news about like terrorists were using certain apps to communicate with each other. And they were saying like the FBI, the CIA, the NSA were all, I think the public thought, oh, well, the FBI can get into them, or, can break into those apps, and nope. No, nobody can. Okay, I mean, it can't. It just doesn't happen. All right. So even like iPhones, the encryption on iPhone, like you've probably heard this. Like if someone locks their phone and that's it, like nobody's getting into that phone. Like it's just the way it is. So, all right, I went off topic. Sorry. The idea of factoring now, right, with numbers is just breaking it down into two simple numbers. The idea of factoring for us in here is going to be slightly different. So let's say I start, I'm going to put this on the side here just so we have it as a reference. 3 times 5, right? That gave us 15 can be written as 3 times 5. Multiply these together, we get this. I want you to compare that to this. What if I told you I had x and I want to multiply that times x plus 3? If I multiply these two together, I get something, right? What would I get if I multiply this? So you have to distribute, right? Mm-hmm. So x times x gives you x squared. And then x times 3 gives you plus 3x. So just like over here, if we start with 15, we can break it down to 3 times 5. Over here, if you start with x squared plus 3x, that can be broken down into two things being multiplied. And that process is what factoring is all about. Okay, so to do this operation of factoring with these expressions, there are a bunch of techniques that you can learn to factor. The first and most basic technique for factoring is called greatest common factor. That's like the first thing you ever have to learn. And that's what I want to talk about today, is this idea of greatest common factor. So I need a new page. So greatest common factor, which we abbreviate this because we don't like writing that out over and over. GCF. If anybody's interested in what I was talking about, go Google RSA encryption. RSA stands for the 3 initials for the last names of the 3 guys who came up with the encryption algorithm. All right, so here we go. Greatest common factor. So the idea, again, I'm going to give you something, and then I want us to be able to break it down to 2 things. And so let's go with this one. And let's go with the one we just had, x squared plus 3x. So the idea of greatest common factor is what you're going to do is you're going to look at first of all, how many terms you have. So does everyone agree I have two terms? Terms are always separated by addition and subtraction. So I have one addition symbol, which means I have two terms, right? Right there. And so I have two terms here. So what I need to do now is I need to look at each term and see what do they have in common? What is the greatest thing that they have in common? So let's look at numbers first. The number in front of x squared is 1, and the number in front of x is a 3. There is no number that divides into 1 and 3 other than 1. Do you all agree with that? 1 is the only number that goes into both of those. And so the only thing they have in common in terms of a number would be the number 1. Right, so I'm going to write that down. They both have GCF. Okay, GCF. What do they have in common? They have a 1, right? They both have a 1. Now, let's look at the letters. Do they both have at least one X? They both have at least one X. Do they both have two X's? No. So what do they have in common? Just one, right? So they have one X in common. So one X is what we will refer to as the greatest common factor. So what you do next is you take this expression and you say, okay, this thing is equal to, and here's where I'm going to try and break it into two pieces. All right, this is where I'm trying to split it, just like we took the 15 and split it to 3 times 5. Here's where I'm trying to split it. The first thing it's going to split into is the GCF part. This is the 1x. And then, very important step, you put a set of parentheses. And in the parentheses, you have to give yourself enough space for two terms that will go into that parenthesis. So now you play a little game in your mind, all right? You think about, if I distribute through, I'm going to have two things here. When I distribute this first thing through, 1x, when I distribute to this question mark, I need to get back x squared. So what would you need to multiply 1x by to get x squared?
X.
X. Okay, so that should be an x, right? And then you play the same game. When I distribute here to here, I need to get a positive 3x. So I need a positive 3, I have a 1. How am I going to turn the 1 into a positive 3?
Multiply it by 3.
By 3, right? By positive 3. So I'm going to put plus 3 right here. And then do I need an x?
No.
No, it already, like this already has an x in it, right? So all I was missing was the 3, and that will create the 3x. And that's our answer. And you can always check your answer, right? You can check your answer by actually distributing through, and you should get back the original expression. Okay, that was a very basic one. Let's try something a little more complicated. Any questions on that one? Okay, I want us to factor the GCF. How many terms do you see?
3.
3. Okay, so look, if you wanted to right now, you could already tell yourself, look, I'm going to have this parenthesis. I'm going to have enough space for 3 things in there. And out here is going to be my GCF. Okay. So we need to find the GCF first. So I always like to start with numbers. So let's see. Robert, you want to go? I'm going to just go through the screen today. Robert Steele. So what number do you see these all have in common?
3, sir.
3, right? And that's the biggest number that they all have in common, right?
Yes.
Like 15 and 30, 5 goes into both of those, right?
But not 3.
But not 3. So you have to go with the biggest number that goes into all of them. So 3, okay, good. All right, how about Angelique?
X squared.
X squared. So the first one has 4 x's. The second one has 2 x's. and the third one has 5 x's. So what do they all have in common? X squared.
X squared.
Good. Good job. Okay, so that's it. There's nothing else. I put the 3x squared on the outside. And then I play this game, right, where I have to figure out what I multiply by to get these 3 pieces. Now, some of you are going to be able to just do this by just looking, right? Now, there is another way to do it where it's a little less like kind of, well, you still have to think, but it's not, this is just kind of another way. What you can do is you can rewrite this problem over here and divide each one of these by the GCF. I've seen it taught this way. I normally don't teach it this way, but if you do this, you'll be able to figure out what these 3 pieces are. Let me try it here. If I do this, the 3's cancel, I get a 1. And then x to the 4th over x squared becomes x squared. Because we subtract, we take 4, subtract 2, we get 2. On the next one, we have negative 15 over 3, that gives you negative 5. And the x squareds cancel, so you just get negative 5. And then you have over here 30 divided by 3, that's positive 10. And then these two together, you get x cubed, because again, 5 take away 2 gives you x cubed. That's what should go in here. You could also do it by just, like I said, like we did the previous one, you ask yourself, what do you multiply this by to get this, right? So the only thing missing here, I already have a 3. I need an x to the 4th, I have x squared, so I'll need x squared here. Riley, does this make sense, Riley? Yes. Here to here, I need to turn a 3 into a negative 15, so I need a negative 5. And x squared turn into x squared, well, it's already x squared, so I don't have to do anything else here. And then here to here, I need to turn 3 into positive 30, so I do positive 10. And then x squared into x to the 5th, so I'll need an x cubed. Y'all see how this gives you the same answer? Same thing. I don't care which way you do it. Just be able to do it. Any questions before I give you? I'm going to give you a few to work on your own. And if you already are good at this, you don't need to worry. I mean, you're good to go, right? So why don't you try, not necessarily all of these, but I think the ones that would be good for you to do, probably 20. And 23 and 25. There we go. I'll leave these up. Why don't you take a minute or 2 or 3 or 4 or 5 to see if you can do the GCF on all 3 of these.
What page was that on again?
This is in our packet on page 230. Yeah. And these are actual homework problems that I'm doing. So when you do the homework, you can go back through and do the ones I didn't do. And if you want more practice, you can actually go up to the notes on this where you have some here. These are actually good ones too. But focus on the homework ones for right now. And I'll give everyone, I don't know, let's see, let's go till about 10:04, and then I'll call on 3 different people to see what you got. We don't have a Grace. Grace, are you here? Grace?
Yeah, I'm here.
Okay, did you take the test?
Yeah, I took the test.
Okay, all right. I just have something on my roster here. Let me check. I need to
Okay.
check to make sure you're on my roster because I have something on here that. Let me go check while you're doing the problem.
Okay.
Okay, you're there. No worries. Does anybody have any questions? Okay, I think that's enough time to get us going here. So Grace, since I don't think I've ever called on you. Let's go with Grace.
Okay, we're doing 20.
Yeah, sure.
Okay. You just want me to tell you my answer?
Yeah, let's just start with your answer and then we can go from there.
Okay, so I got 9x cubed.
Okay.
And then inside the parentheses, I don't know if I'm saying this right. I
That's
got
fine.
4 plus 10x squared minus 8 to the or x to the fourth power. I don't know how to say that.
Okay, that's right. No, you said that fine.
Okay.
Okay, so Grace, what was the hardest part for you? If there was a hard part, what was it?
There really wasn't one, honestly.
Okay, so you had no problem figuring out the biggest number?
Yeah.
Okay. So yeah, I think for most students, the most challenging part would just make sure you get the biggest number that goes into all of these. Because there are numbers smaller than 9 that go into all of these. Like 3 goes into all of these. But you're trying to get the biggest number that is the divisor of each of these numbers. So 9 is the biggest one. And then X, you have 3 X's is the most that appear in all of them. So X cubed, and then you distribute through. All right, anybody disagree with this answer? I'm not even looking to check.
I disagree.
I got 18.
I had 18.
I got 18 as well.
Oh, for the last one? Maybe, wait, 8?
No, I
18
got,
goes into all the numbers.
yeah.
Oh,
Like 18x cubed goes into all of them.
okay, so there's a bigger number.
Mhm.
Yeah, I'd use 6, but I didn't know you could use 18.
Okay, so Grace, let me ask you. You pulled the 9 out, right? So you saw 9 as the biggest number.
Right.
Look at these numbers that are left in here. One way to check to see if you've got the biggest number is to see with the numbers that remain, is there a number that goes into those? And can you see these are all even numbers?
Right. Okay. Yeah, I get that.
Okay, so we could pull an additional 2 out. So Grace, if you did this step, let's say on a test, you don't need to start all over. All you have to do now is take a 2 out with the 9x cubed, and then pull the 2 out of each of those. Right? And
Right.
then, of course, you put the 2 and 9 together and get an 18. But now when you look at the numbers 2, 5, and -4, now there's no more numbers that go into all of those.
Okay. Yeah, that makes sense.
Good? Okay.
Thank
So,
you.
yeah, what I always recommend is that if you're not sure, then go with the number you know, right? Like if, let's say you started with, I don't know, 3, and then look at what remains and see if you can pull something out of those, and then just keep going as long as you can go until you get to a point where you definitely are sure there's no number that goes into those anymore. Okay, good. I think that was good that we went through that. How about, let's see. Shazia? No. I see Shazia. All right, how about Gender Rose?
I honestly stayed a little on the first one, so I don't have the answer to or 23
You
or
don't have
25.
you don't have the next one yet?
No, sorry.
Okay, well, let's go through it together, okay? Looking at the numbers 14, 12, and 8, what is the first number that you can think of that goes into all of those? Start small and work your way up. Put you on the
Sorry.
spot.
So I was thinking about it. It's I think it's like 2x.
2, okay, so 2 goes into all those. Let's try it. 2 and then x. Okay, so 2x. And so let's see, we need enough space for 3 things here.
6 and 4.
Say again?
Oh, so I think it's like you can divide them all by 2x, then you can get you get 7x squared minus 6x and then 4.
Plus 4. Okay, so now we just check, right? Gender Rose, we just check 7, 6, and 4. There's no number that goes into all of those other than 1, right?
Yeah.
So, and notice also we don't have any more x's in all of them, right? So we didn't miss an x. It was perfect to pull just 1 x out. What do y'all think? Y'all agree with this? Does it look good? Okay.
Yeah.
All right. And then for the last one, I'll just take a volunteer for the last one. So who wants to give me this one?
I'll do it.
Go ahead.
So I got a little confused with this one because there's not an X in all of them. So, but what I got was that the GCF is 8.
Okay, yeah, so we don't have to have an X, okay? It's okay
Okay.
if it's just a number.
So I got 8, and then it would be, in the parentheses would be 4x squared
Mhm.
minus 2x plus 1.
There you go. Looks good. So just remember, a GCF is the greatest thing they have in common. So if that happens to be a number, it's a number, right? If I gave you a problem like this, x cubed minus 2x squared plus 3x. If I ask you for the GCF of this one, you would have only an x in common, no numbers, just x, and you'd be left with x squared minus 2x plus 3. So it's okay if you have just an x,
Okay.
or if you have just a number, or both x's and numbers. That's all okay.
Can I write down that example real quick?
Yep. All right, so I think, the best thing for you at this point is to just practice this more, so you can just get used to the repetition of it and being careful with picking the numbers. And I believe I'm
And you
ready.
said to make sure to go with the highest number, right?
Biggest number, yeah. So like earlier when we pulled just that 9 out, this would be factored, but it's not completely factored. It's completely factored when you pull the 2 out also and get the 18. So like on a test, if you did this, you would get partial credit, but you wouldn't get full credit because it's not completely factored. All right, y'all ready to move on? Okay, so we're changing gears here, switching gears. We're going and moving to the section on lines, which is going to be on page 53 on the packet. So we're going way back into the packet to the earlier parts of it, page 53. And I'm actually not even going to start doing this out of the packet. I'm going to just start writing my own notes. Where are we here? Yeah, I'm just going to start doing my own notes. So what we want to talk about now are linear equations in one variable. All right, we're going to talk about linear equations. Sorry, and I did not mean to say one variable. I meant to say 2 variables. 2 variables. Linear equations in 2 variables. So what is a linear equation in 2 variables? Let me give you an example. What if I tell you that I take some variable x, I add to it some other variable y, and I get an answer of 10. Okay, this is a linear equation in 2 variables. What makes it linear equation 2 variables? Well, first of all, it's an equation because it has an equal sign, right? It's linear because, and this is important, because when you look at the powers on the variables, there's 1s here. Now, we don't normally write the 1s, but we need to understand that the x is being raised to the first power and the y is being raised to the first power. When you see a power of 1 on both of the variables, then we are talking about linear, okay? Linear means powers on the variables are 1s, okay? If one of those happened to be a 2, then we'd no longer be talking about a linear equation. The last thing in this is that I said in 2 variables, which means that there are 2 variables you see, x and y, right? Do not confuse that with this. If I gave you that, that is a linear equation, but in 1 variable. There's only 1 variable in there, right? X. That's not what we're looking at. We're looking at this instead. Do y'all see the difference between those 2? Okay, so a linear equation, 1 variable. So I want you to just look at that equation, okay? And I want somebody in here to voluntarily give me a value of X and a value of Y that I could put in here and make this thing still be true.
5 plus 5, right?
5 and 5. So you're saying if X is 5 and Y is 5, then that would mean it's true. Do you all
Would
agree?
6 and 4 also work?
Yeah, that's not the only answer, right? There's
Mhm.
another answer. If, what did you say? If,
6 and 4.
so if X was 6 and Y was 4, it would also be true. There any others?
7 and 3.
7 and 3.
You can just keep on going down the whole, like,
Yeah, I mean, like you could go, literally,
9
you
and
could do
1.
this for the rest of your life, right? And you would die before you ever get to the end because you'd have an infinite number of possibilities. Do y'all agree? Now
Yes.
compare that to the one that I crossed out over here. If I asked you to take this equation and solve it, right? There's only one answer. You subtract 4, you would get X is 6, right? And we're done.
Yep.
One answer. For this linear equation in 2 variables, there appears to be an infinite number of ways we can make the equation true. Y'all understand that? There's an infinite number of ways we can do it. We can also use negative numbers. Nobody gave me any negative numbers, but couldn't I do like X is negative 20 and Y is 30? Like if I add those two together, I get
I
10.
think with 11 and negative 1.
You could do 11 and you could do negative 1, right? So this list goes on and on and on and on and on. Infinite number of answers, right? So what we decided as human beings, all right, we said, hey, look, for an equation like this, maybe there's a way we can visualize all of these answers, because visualizing one answer like this is easy. If I said, hey, go to a number line, where is 6? Well, here's 6. I could put a dot right there and I'd be like, oh, that is the answer to that equation. It's very easy to visualize that. Just draw a number line, put your answer on it, draw a dot, right? But we were sitting here and we're like, how do we visualize all of these infinitely many answers? And what we decided to do was draw what we call a graph, right? We created this thing called the XY plane, or the coordinate axes. What we decided is that this we would call the x-axis, and this we would call the y-axis. And then what we would do is we would look at these answers and we would treat them as points on this plane, on this flat sheet. And so what we did is we said, all right, see this answer 5 and 5? I'm going to write it as what we call an ordered pair. An ordered pair. And when I write an ordered pair will always be the x and then comma, then the y. So this would be 5, 5. This one would be 6, 4. This one would be 7, 3. This one's negative 20, 30. This one is 11, negative 1. And then I could keep going, right, with this infinite list. Then we decided, well, we came up with a way that we would graph these, okay, on here. So if I wanted to do the point 5, 5, that means I move to the right 5, and I go up 5. And I put a point right there. That's the point 5, 5. Then I could put the point 6, 4, which would mean I go to the right 6, 6 for the x, and then up 4, 2, 3, 4, and that would be another point that would represent that answer.
The line would just go down, right?
Well, you said line, right? You said the line would go down.
Mm-hmm.
Well, you're assuming it's a line, right? You're
Yes.
assuming that this is going to create a line. Let's do a couple more points. And I think if we do a couple more points, we'll convince ourselves that all these answers lie on a line, don't they? Well, let's see. 7, 3. So we go out to the right, 7, we go up 1, 2, 3. Hey, look, it's starting to look like these do lie on a line. We didn't do the 0.8, but if we tried it, if we did 8 in there, we'd have to get 2 for the y, right? 8 plus 2. So that would mean to the right 8 up 2. All of these appear to lie on a line, right? They appear that they lie on a line. And it turns out that they do. That's why we call it a linear equation. It's called a linear equation because when you draw all the answers, if you could spend the rest of your life drawing all the answers, they will all create a line. So this line is actually made up of an infinite number of points. That's what a line is. It's an infinite number of points. Okay. Every single point on that line is a solution to that equation. Every point. All right. So that is the basic idea of a linear equation in two variables, is that when you graph them, you get lines. And so what we're going to do now is we're going to come up with we're going to have two different methods that we will use to graph lines. Two methods. Today, with the 20 minutes I have left or so, 25 minutes, I'm going to teach you the first method for graphing lines. All right. This first part was just to convince you that, look, if you ever have a linear equation with two variables, all the solutions together create a line. Now let's talk about how we can do this more efficiently, because doing this table or doing all that, plugging in, is just kind of a pain in the butt. So we want to do a short method. So before we do it, I want to point out some properties of lines. Okay, if I draw a line, all right, so I'm just going to come in here with a random line. I'm just going to make it up here. Boom, I draw a line. There it is. Okay. If I draw some random line, then is it always going to hit the x-axis somewhere? If I just draw a random line, will I always hit the x-axis?
No.
No? Okay, so when could it possibly not?
When it's a zero property, perhaps?
It's negative.
How about if I draw a line that's completely flat and horizontal like that? Would that ever hit the x-axis?
No.
No.
No, right? But if it's not flat, right? If it's not horizontal, then must I hit it somewhere?
Yes.
As long as it's not horizontal. So I'm going to write this down. If the line isn't horizontal, then it must hit the x-axis. We call that an X-intercept. Anywhere that the graph hits the x-axis is called an X-intercept. So as long as it's not horizontal, right? As long as it's not perfectly flat like that. Horizontal, think horizon, right? Horizontal. As long as it's not horizontal, you give it any sort of pitch, any little pitch to the line, right? Then it's eventually going to hit the x-axis somewhere, even if it's way off on your graph, like way, way far away. Okay, everyone agree with that? What about a y-intercept? Do you think it's always going to hit the y-axis somewhere? Not always.
Not vertical.
As long as it's not vertical. See, because you could draw a line that's vertical and it would not necessarily have to hit the y-axis. So we need to make sure we're clear on that. If the line isn't vertical, as long as it's not vertical, then it must hit the y-axis. And we call that a y-intercept. Understand that? Now, let's say that it does, okay? Let's say that we have a line that's not vertical and not horizontal, okay? So it hits the X and Y axis. Come on, stop. Let's say we have a line that's not vertical and not horizontal. Then it must hit the X and the Y axis, right? What can you tell me about that Y-intercept and that X-intercept in terms of what the X and Y values would have to be? So let's start with the X-intercept. Can anybody tell me, if you have an X-intercept, what something about this point that's special?
Y value is going to be equal to 0.
The Y value has to be 0 here. So think about it. If you're on the X-axis, then you're not moving up or down, are you? Which means your Y has to be 0. Now the X can be kind of anything, right? Because it just depends on the line, where the line puts it. But guaranteed, if you're on the X-axis, your Y has to be 0, right? So Y must be 0. Similarly, if you hit the Y-axis, right, then what can you tell me about the point?
X will always be 0.
X will be 0. Good. And then the Y will be something, we don't know what it is, right? But the X has to be 0. Emily, you're not driving, right?
No, I'm not driving. I'm on
Okay.
campus in my car.
Oh, okay. I was like, I haven't seen your eyes on the road.
Yeah, no, I'm not driving.
Okay. It's like, all right. Okay. That's an important idea here, all right? That this is a Y-intercept, right? This is your Y-intercept. I'm going to put Y-int to represent Y-intercept, and this right here is your X-intercept. So let me just say this verbally one more time. If we're looking at an X-intercept, the Y value has to be 0, doesn't it? For an X-intercept, the Y value has to be 0. If you're looking at a Y-intercept, the X value has to be 0. Agreed? Just from the picture. So we're actually going to use that to develop our first method for graphing lines. That idea, that concept. And it is called the intercept method. Intercept method. Or sketching lines. Now, this method, it only works if it's not vertical or horizontal. If it's vertical or horizontal, this method's not going to work. Okay. So here's how it works. And I think the best way to see it is just to do an example. All right. So I'm going to give you an example of a linear equation in 2 variables. So here it is. 2x minus 6y equals 12. I would like for you first to understand, I should put instructions here, sketch this. I want you to first understand that you're looking at a linear equation in 2 variables. Does everyone agree with that? That's an equation, has 2 variables. They're both raised to the first power. So it's a linear equation in 2 variables, which means that all of the solutions to this must lie on a line. Okay, they have to. So it's our task to draw that line. So what I'm going to do first is I'm going to just find the X-intercept. How do we find the X-intercept then? Well, what do we know? What did we say about the X-intercept? If you're ever looking at the X-intercept, what has to be what?
Y has to be 0.
Y has to be 0, right? So what I'm going to do is I'm going to now replace the y with 0, and then solve. So let's do that. I'm going to write the equation down. I'm going to replace the y with 0. Okay, see, I've replaced that y with 0. I didn't replace the x with 0. I replaced the y with 0. That's how we find the x-intercept. So it's opposite. You're looking for the x-intercept, you set y to 0. And then we just figure out what this is. So this goes away. All you're left with is 2x equals 12. And that's a good old-fashioned linear equation with one variable in it, right? There's only one variable now. So you just solve it the way we've learned to solve this. We can just divide both sides by 2, and we get x is 6. So here's what I know. I have an x-intercept where the x is 6 and the y is 0, right? This is a point on our, this is one point on our line, right? If we just had one more point, right? If I give you 2 points, you can always draw a line between them. So if I just had one more point, I could draw the line. Well, the other point we're going to get is the y-intercept. And once we have that one, then we just draw a line. So to get the y-intercept, we do the same method. We replace the x with 0 this time, and then solve. So I write down 2, replace the x with 0, minus 6y equals 12. That goes away. We get negative 6y equals 12. And now again, we have a linear equation with one variable. We can solve for y by dividing both sides by negative 6. And just be careful with your signs here. This is where a lot of students make mistakes, just with the simple signs. Our answer is negative 2, right? And that means the point on our graph is going to have 0 for the x coordinate because it's a y-intercept, and then negative 2 on the y. So this is our x, this is our y, and this should be a point on our graph. Any questions on what I've done there? Graph time. All right, I'm just going to draw it. So here we go. All right, so to do this, I'm going to start with this x-intercept. I'm going to plot the point 6, 0. So I go to the right, 1, 2, 3, 4, 5, 6. There's 6. Oops, I didn't go far enough. 6, 0, that's my x-intercept. And then 0, negative 2. So that means I don't go left or right. I just come down 2. And then once I have those 2 points, I connect them with a straight line. If I can ever get this to look right. There we go. That is the graph of this line. Okay. Now, let me ask you a quick question here. Go back up to this. And I don't want you to plug anything in. I don't want you to try and plug these numbers in your mind or anything else. I want you to just think about this graph. And I want to ask you, is negative 7, 5, if x, well, yeah, is negative 7, 5 a solution to this equation? Don't try and plug it in. Is it possible for this to be an answer?
No,
Why not?
because that has a negative 7. So wouldn't that, since those are odds, they wouldn't go into those because they're evens in our sketch?
Yeah, but unless you plug it in, you may, I mean, it may turn out to be, it may turn out to work.
Oh, okay.
I'm trying to get you to see this. Go ahead, Nix.
It's because with the negative 7, it would put it on the left side of the y-axis, and on that side they're all negative, so the positive 5 and the y-axis would not work.
Yeah, do y'all see that? if you look at this point, -7, 5, that means to plot this point, you would have to go to the left and up, right? But your graph is down here. So that point couldn't live on this line. Does that make sense? And I could eliminate anything over here, right? Pretty much anything over there wouldn't work. So if I ever tried to plug, I mean, all these points over here, every point you could ever come up with over here would be negative here and positive here. Agreed? So I can tell you right now, if you try and plug any negative number for X and a positive number for Y, you're not going to get a solution. I'm just trying to show you how having the graph is actually gives you a lot of information about what's going on. Okay, we have about 9 minutes. Here's what I'm gonna do. I'm gonna give you one to do. I'm gonna give you two to try on your own. Use the same method, okay? The first one is gonna be a little easier. The second one is gonna be a little more challenging. So let's go with this. Negative 4x plus 20 equals 5y. And then the other one is negative 1/3 x plus, let's go minus 1/2 y equals 5/6. Okay, so the first one is very much like what we just did, okay? Go through the process. The second one, I'll give you a hint, okay? My hint on the second one is, before you even begin, clear the fractions. Clear the fractions out. We've done that before when we were working with expressions. We multiply both sides of the equation by something that gets rid of fractions. Once you do that, then you can continue the problem. All right, those are the two. You work on those. I'm going to copy these and put them on the previous page. So if you need to refer to what steps we used, they're right here. Let me stick this right here. Whoa, that didn't go there. I can put them right up there. There they are. Those are the problems there. And then there's the problem from earlier. Okay, let's go ahead and work on this. We don't have a whole lot of time, just a few more minutes. So see what you can get done, at least hopefully the first one. Desiree, do you have some time after class to talk with me for maybe a minute or two?
Okay.
You could try, yes?
Yes. I mean, yes.
Okay, it'll be quick. We'll keep it short. I just want to talk to you before we get to the weekend.
Okay.
Okay, thank you. I just launched the poll. I don't want you to respond to the poll until you're done with the first one. If you finish the first one, just click choice 1. Okay. I'm just trying to figure out how long it's taking people. If you haven't done it, just wait.
Should I move the 5 over first?
You do not have to.
Okay.
You can just follow the method, because once you replace the y and the x with 0 in those methods, you should just have an equation to solve.
Okay.
Quick question. You said that when we were done with the first problem to go to the poll, right?
Yeah, I just want to see how long it's taking people to get through the first one.
So do I just, do you just click?
choice one?
Oh, okay. Okay,
Yeah.
thanks.
Yep. Yeah, so right now we have 10 out of the 23 students in here have finished the first one.
So during class, my computer started glitching, so I had to go through my phone and I have to take it back today. So it's not letting me see what the choices are besides choice 1 and choice 2 on the poll.
Yeah, it's just two choices. It's just, I'm just choice 1 and 2. It's just to let me know when you're done. Don't worry about it. Don't worry about it. I'm going to end the poll anyway. Okay, so most of you are done with the first one. So here's what we're going to do because we're running out of time. Just finish those up and keep them handy because I may take those as for credit for something. Don't throw it away. Don't lose it. For homework, here's what I'd like for you to try. We haven't done everything we need to do, but I'm going to point out some problems for you to attempt here. So you have to be very specific here. Here we go. Okay, page 62. Number 9. We can try 10. Do 9 through 12. Just to get us started. Okay, that'll be it for this section. Now also make sure you do the homework from the previous section, greatest common factor. And that was, let me see, that was, so page 62, 9 through 12, but then also finish up this work on page 229, 1 through 25 odd. You've done a lot of that already, but just finish up the few things we didn't do. Any questions?
Thank you, sir.
That's it for today. So everyone have a great weekend, and I will see you
You
next
too.
week. Okay.
Have a good weekend.
You too.
Bye.
Have a good weekend.
Have a good rest of your day, sir, and weekend too.
Bye, thank you.
Real quick, you
Have a
said
great week.